Alright, so before we start, do you have any questions? No?
Oh, I have one question.
Yes,
Did you say,
go ahead.
maybe I misheard, that there were already a few papers up on the course website that would be for...
Yes, I will talk about that. I will talk about that. So I've created this assignment 0 and it's I think due tomorrow and it won't be graded, but I think it's a requirement for some of you who are getting a financial aid. So if you're not sure, check with like from where you're getting your financial aid. I think it's a requirement you should finish this assignment. Okay. And so the class, it hasn't changed, so from now onwards we will meet here, 103. That was pretty small. So regarding next week, so Tuesday we'll have this presentation from Kevin. He will present his ICCV paper and I want you to go through this paper before the class, and the good thing is you don't have to write any report and it's not like part of the coursework but just the first presentation. So what we will do is like he will present for first 30 minutes, then we can discuss that paper. If you have any questions, then we can answer those. So before the class, just go through this. I think it's on the course website and you can find the link there as well. And let me know if you couldn't find this paper. Then on Thursday, this will be like the first paper for the class, and one of you will, I think either Ishan or Rohit is going to present this. Yeah. And so for this, there is this report submission. So we'll have to make a report submission. And yes.
Sorry, this is a bit of a side. Are these notes going to be posted?
Sorry, can you speak
Will
louder?
these slides be posted? The slides we're looking at right now, will they be posted as well? Maybe you already-
These slides, they are already
Yes.
on the website.
All right, thank you.
They are already on. So for this paper, you will have to write a report, and the deadline for the report is just before the class, before 3 p.m. And the format we already discussed in the last class. So any questions about this report submission? So I opened this poll, let me check like, so all of you finished this or? I think last time it was 50-50, but this time when I checked, most of you want to do like one per week. Probably that's because just 50% of the report. Just give me a minute. So yeah, I think almost all of you, 25 of you are saying like one per week. So that's fine. And so what will happen is, so like next week we only have one paper. So we'll have to make the submission. So there is no choice. But I will make sure like from next week onwards, you always will have 2 papers so that you can choose like one of those. And so I checked the calendar and I don't think any of the holidays falling in is clashing with the classes. So that's good. So that's done. Now I will be away on these dates, 23rd, 11th, 13th. But I don't want to miss these classes, these classes because we already have an enrollment of 32, but we have I think 26 or 25 slots. So at the end, what we'll have to do is I think 2 of the students will make the presentation on the same day, and if we skip in between, then it will be like more tighter. So what I want from you is I want alternate day and timing when all of you are available. So let's start with like for the 23rd Jan. So we have a discussion session on Wednesday, right? 4:30 to 5:15 or 4 to 5:15. So is everyone like all of you available during that time, or you have classes or any other engagement? So 4 to 5:15 Wednesday. 450.
1.5.
415. 415. Okay. Alright. Yes.
If we have like work, is it required to go to like extra classes?
Okay. So you mean you won't be able to attend on Wednesday?
Like if we have like a job or something that we have.
Yeah, I mean that's fine
Okay.
because we don't have any grades for attendance, so it should be okay.
Okay.
But so you're saying that apart from those two slots, when we have classes, you won't be able to make it, or
I personally won't be able to. So.
okay? All right, that's fine. Anyone else? So let me go 3, 4, 5, 6, 7.
Is it the coming Wednesday or which Wednesday?
This is 23rd. Next week.
We might have a reading group at our lab, so I don't know. Refresh.
Yeah, I think that should be fine. Yes.
I'm confused, this is a makeup for what?
This is a makeup for 23rd. Let me check 23rd. I think it's Tuesday next to next week. And next to next week Thursday. So then it will be 22nd of January. So instead of 23rd, we'll meet on 22nd.
22nd is Wednesday.
It's Wednesday, yeah. These are just 24. I think there are still 7 people missing. But so let's do this. Let's make that 4:15 to maybe 5:15. We'll try to wrap it early. So that should be fine with everyone. So that's good for you. Yes.
All of those dates? No.
No, just for 23rd.
Okay.
And probably so 11th, 13th. I'm not sure. Probably I will try to avoid one of those. But for the other, I think we'll have to do the same. So you are saying you will have issue like on 11th or 13th?
Just comment all of
I have a class on Wednesday during that time.
You have a class on Wednesday?
Yeah, so the 22nd I will do for me.
Oh, okay. I just asked and you didn't say anything.
Oh, we like that as a 23rd Wednesday.
Okay.
No, it's makeup class for 23rd.
Oh, I see. Yeah, I can't make the 23rd.
You can.
Say no.
You cannot make it. So Wednesday you have a class. So what's the timing for the class? What's the timing for the class?
I work at the seminar with like 3:30 and 6. So like that whole 3-hour block.
So that's not good. How about Fridays? So Friday, let's say 3 to 4:15.
No office hours during them.
Mm-hmm.
I have office hours during them.
Office hours. Okay.
I have meetings.
Alright. So what if we make it like little early on Wednesday?
Like how much earlier?
Maybe 2 start at 2.
Yeah, it seems.
If class. Okay, so let's make it. I think.
Maybe you can send a poll later.
Sorry.
Maybe you can send a poll and see.
Okay, I will do that. I think that's a good idea. Okay. I will give you some slots and then you can fill it up. We'll see what happens. So yeah, one of you, I think Steve was asking whether you can call me Yogesh. That's fine. That's my name. You can obviously call me that. So before we start, any questions? Any administrative stuff? Any other questions you have? Oh, we are good. Okay, good to go. So what we are going to do is we have 2 different parts and we'll see like how much we can cover. The first is I will try to cover the basics of convolutional neural network, how these works, and we will go through a case study of this AlexNet, which was like the first neural network which gave us good results in image classification task. And after this, in the second part, we'll see like how we train these networks, what are the issues which you face, and what are different other variants of like the CNNs apart from this AlexNet. Then we briefly also cover this recurrent neural network, and then maybe couple of slides of this generative address network, because this GAN thing, this adversarial learning will, I think you will see in almost all the papers they will use it, so I think you should know what this is. Now before proceeding, how many of you already know what AlexNet is? Okay, maybe otherwise, how many of you don't know what AlexNet is? So for those who already know, I think be patient, that's fine. But for those students who don't know, then we'll have to cover this very in detail so that they can understand. So be patient. And now, how many of you know like how? So you know AlexNet. How many of you know how a convolutional neural network actually works? All of you. Okay. Probably then we'll go a little quicker, and if you guys have any questions, you can interrupt in between. That's perfectly fine. So CNN, they are simply another class of neural networks, and they take images as input and produce some kind of output which makes prediction about the input image, and the prediction could be anything. It could be like what is present in the class, or it could be if we are looking for any particular object, where that object is located, or if we want to make some other predictions like what's the fine boundary of that object, we call that image segmentation. So all these kind of outputs. And the common thing is like the input will be an image, a 2D image. So this is like one simple example of a CNN, and here you can see that the input is an image. It will have some kind of resolution, X by Y, and then it will have 3 different channels. So for R, G, and B, that's the standard we use for CNNs. You can of course use like other spaces as like HSV or something else. That's also fine. Now, given this input, this part is like the CNN, and it has like some set of components, and we will go through these in detail. We'll have some convolution operations. We have layers like max pooling layers, which try to reduce the size of the input data. And then, so this part is like the convolutional part. And then what we do is, whatever features we have after the convolutions, this is like a standard, we call it fully connected layers, but it's nothing, it's like the standard neural network, where we have some neurons, and then we have fully connected layers. Each neuron is connected to every other neuron, and we learn weights for those. And at the end, we try to make some predictions, so that's the output, like what we want to predict of this class. So let's say if we are doing image classification, then we'll have some set of classes, let's say 10 object classes. So we'll make prediction for each of those classes, and these will be probabilities, usually between 0 and 1, which will say like of certain confidence that this object is present or not. So in case of if it's a single label classification, which is trying to actually just predict one category, then what will happen is only one of this is going to be very high. I mean, it will have high probability, others will be close to 0. But if it's a multi-level classification, then there will be multiple objects present. Then in that case, what might happen is multiple predictions be like close to 1, and the rest which are not present will be 0. So those are just some basics. And so this is not like entirely new. CNNs, they were initially introduced in 90s, late 90s, and this was like the first architecture, and this was like used again. I think the AlexNet architecture is also similar to this. And here what they try to do is, instead of a colored image, they have a binary image, grayscale image. So single channel, and then again those convolution layers. They have subsampling instead of max pooling, again convolutions. Fully connected, they try to make prediction. So they tried like 2 things. One was character identification, and letters, 26 letters. So you have 26 predictions. The other was digit classification. In that case, you will have 10 predictions for each of the digits. Now the same architecture was used in AlexNet, almost similar, and this was like the first paper where we have like very strong results. What they showed is in this ImageNet large scale recognition challenge, they improved the accuracy by a big margin, and they showed like error rate of 15%, and the second best entry, which was like non-deep learning, was 26%. That was a huge gap. And after that, we have seen like in almost all the problems, everyone is trying to use these deep networks, and it doesn't have to be just classification. it can be used in many other problems as well. So classification, of course, like if you want to predict like what classes are present, that's a standard problem there where all it started. It can be used for object detection. This is again, apart from saying that which object or which objects are present in the image, we also have to localize where the object is present. And that localization could be a bounding box, just covering the portion where the object is. It could be a very fine boundary, which we call like segmentation. So here we'll see like it's not just like a bounding box, it's like pixel level. Each pixel is saying which object this is. It's also used for image captioning. So given an image, if you want to describe in textual format what's happening, so that's a task like image captioning. You can solve that as well. So this is again an interesting problem of style transfer. So what this is trying to do is, if you have a style, you want to transfer this style of painting or photograph into an input image. So if you do the transfer, so this is also like you can do using CNNs. Now all those problems were based on RGB images, but you can use CNNs for other problems, other domains as well. So not just images. For example, NLP. So if you have to do text classification, of course you can use CNN, and the way is like you take each word and you can get a vector. So there's a word to vector. I think you know that. Everyone have heard of like word to vector? Alright. So word to vector, yes.
What's the term? I'm sorry.
Word to vector. So what it does is like given a word, it will give you a feature vector of like certain length. It could be 100 dimensional, 200 dimensional. So it's like representation of that textual word in terms of bits 0 and 1s. You don't have to know that, that's fine if you don't know, perfectly fine. So given a sentence, what you can do is use word to vec, get the features, and this is again a 2-dimensional map and you can apply CNNs on that. Similarly, like in audio it has been used. You can represent the audio as a spectrograms, and again this is like the image, and you can apply convolutions on top of this. So as long as you can convert the input data type to a 2D format or a matrix format, you can apply convolutions. Even if you don't convert it to 2D format, it could be like a sequential data. Then instead of 2D convolutions, you can do 1D convolutions. Again, those will be convolution neural networks. So similarly, for videos, what we do is instead of applying 2D convolutions, we apply 3D convolutions, because apart from like the X and Y, we also have the temporal extent of a video. Now, the question is like, is it perfect? It's actually far from perfect, and the reason is you can easily perturb your input image slightly and then your network will fail. So for example, in these cases, these are just noise images, and a well-trained classifier is actually classifying these patches as, so this one is classified as cheetah, but you can clearly see it's not anywhere close to cheetah. So this is like one end. The other end is where it's actually called adversarial attack, and what they do is, it will be an image of cheetah. If shown to you, you will say it's a cheetah, but what they do is they will slightly modify that image so that the classifier says maybe it's something else. Maybe it's like a cow or something else. So that's pretty easy. So it's very easy to fool the classifiers which are based on CNN. Alright, so let's go into detail how they actually work. So before we do, like, any questions you have? Okay. So neural network, I think almost all of you know, it's just a series of fully connected layers. You have some neurons in one layer, then you have certain set of neurons in the second layer. All the neurons of the first layer are connected to the second layer, then you learn weights for those connections, and then it's like trained using different optimization algorithms. Now, what's the issue? Why can't we use neural networks to do image classification? So for example, let's say you have an image of H, W, and C. So there's the height of the image, width of the image, and these are the number of channels. So for RGB it will be 3. And so for example, we have 256 by 256 and then 3. So what will happen is, if you have to train a neural network, you will have to actually flatten that image and convert each pixel as a neuron, as an input data point. And that will translate into this almost 196, almost 200k neurons. And then what will happen is, in your input layer, you will have these 200k neurons, and irrespective of how many neurons you have in your second layer, all of those neurons are going to be connected to those, and let's say those are just 1000. So this, like, I think translates to more than maybe 2 million. So that's a lot of neurons, a lot of memory consumption. So it's not practical to actually train these neural networks on top of images. Now, how convolution actually helps in this case? So in standard neural network, it's just a series of neurons and you have weights connecting two neurons. In CNNs, you have volume of features which actually translates from one layer to another. So your input volume is your image. So let's say if it's 256, 256, 3, so that's a volume, right? 3D volume. Then you will apply some transformation on that. That's based on convolution. We'll go through that, how that's done. So let's say you perform some transformation, you will get another volume. So that will be less than that volume or maybe equivalent to that volume. And then you go on. So those are your convolution layers. So what will happen is your input data as volume is like carrying forward to the prediction as volume. So it's not growing. So that's one property. You are moving from one volume to another and finally to the prediction. The other interesting thing is when you perform the transformation of those volumes, you don't have to learn a separate weight to do the transformation for each pixel location or each location in that volume. So whatever operation you are performing at each location of the volume, it can be shared across all the locations. So that's a good thing. That's a good thing because then your memory consumption is not that high and it's different from this transformation. So in this case, if you are connecting this neuron to this neuron, you have a separate weight, right? And if you're connecting this neuron to this, you have a separate weight. So you're not sharing weights. For each neuron, you have a different weight. In this case, you are sharing those weights. So we'll see how we are actually doing that. So before moving on to that, let's try to understand what a convolution operation is. This convolution, it's actually the core building block of any neural network. And so this is just, alright, so let's go through this example first. So this is the input image, 32 cross 32, and then 3 channels. It's the volume. Then we have a filter. We call this convolution filter, and this filter is actually the weight which we will use to do the transformation. So instead of having just one weight which we have in neural networks, we have this kernel. Now this kernel is actually convolved at each of these locations in the input volume, and again this volume could be the input data or it could be like any volume inside the network. So you perform convolution. I will go through this, what this convolution operation is. So at this moment, just bear with me, and the only thing you have to see is like when you convert this kernel at any location, you just get one number. Now what you do is you will convolve this kernel at all the locations. So what will happen is you will get a feature map which you call as activation map as well. So for this particular dimension, if this is the filter size, you will get these many activations. Okay? So this is just one filter. You can have multiple filters, and of course we have in any CNN. So then you can get another activation map. So that taking a filter, convolving it like to each input location, that's called the convolution operation, and a convolution layer in a CNN is actually formed based on that. So this is what we call convolution layer. The input volume, we have some kernel, we do convolution, and that's the output. So I will explain like how we get these as 30, but 6 is, we will have 6 different kernels. So each of the activation will be for one kernel, and that's why the width of this is 6. Now usually in CNN we don't have just one layer, we have a series of convolution layers. So again the input, then we have 6 kernels of this size, 5 cross 5 cross 3.
Question?
Yes.
Are we seeing that as 6 activation maps on the right?
This one?
Yes, is that 6 activation maps each slice in that
Yes,
direction?
it's 6 different activation maps. So each activation map was generated using one kernel.
Yeah.
So now we have 6 filters here. So we get 6 activation maps, and if the filter size is 5 cross 5 cross 3, the shape of this volume will be 28 cross 28. We'll cover this how we get like from 32 to 28. But one thing you should note here is the filter size at each convolution layer should match with the width of this volume here. So if the width of this volume is 3, then the depth of the kernel should always be 3. And the reason behind that is when you apply a kernel at each location, it actually spans the complete width of the volume. So it's looking at all the activations at once. So that's something important to know. Now in this case, if we have 16 kernels, again 5 cross 5, then if we look at 6, it will have to match with this. And we'll get 16 activation maps. The spatial, we will look at like the spatial dimension is reducing. So it started from 32, 28, and 24. The other thing is this 5 cross 5 is how many spatial region of that activation map we are going to cover. Okay. So when I say convolution, let's try to understand what convolution is. So convolution is always performed between two functions. So it's a mathematical operation, and let's say we have a one-dimensional a function which is like just defined in the x domain. So this is just a step function ft. Let's say we have another function gt. So we call this, let's assume this is our input data or input volume, and this is our kernel, the kernels which we are learning. But in this formulation, these are just two functions. Now this plot is actually trying to explain how convolution will work. So that's actually the equation of convolution. If you vary from like negative infinity to positive infinity, you just have to multiply those two functions. Now if the, so we fix this function blue one here, okay? When our red kernel is at this location, then the red function and the blue function, they are not overlapping at all, right? There is no overlap, no similarity. So when you multiply these two, you will get 0. So if you will like monitor this black curve, this is the output of the convolution operation. So what's happening is if there is no overlap, it's 0. If there is a slight overlap, it's increasing. And if you see, if those two curves are perfectly overlapping with each other, it means that those two functions are matching, then it's highly activated. Alright? So what convolution is trying to do is it's trying to match two different functions and trying to figure out if those two are similar or not. So that's the intuition behind using convolution in a CNN network. We are just trying to match patterns. Right? So whatever kernels we learn, it will try to find those patterns in the input image or the input data. And if it finds, it will be highly active. Okay. Any question in this? So that was the mathematical formation. Now let's try to understand how it will work in our CNN networks. So let's say this is the input image. It's pretty small, but that's fine. And it's representing each pixel value. It could be either 0, 0 or 1. But if it's an RGB image, these values will be between 0 and 255. So for now, just assume that the values could be either 0 or 1. That's our filter. And so we will actually learn these filters while we train our network. For time being, just assume that let's say we know what the filter is. And in this filter, like these locations are 0 and these are 1. So what will happen is when we will try to do convolution of this filter on this input data, we are actually looking for this pattern, this cross pattern. So whenever we have this cross pattern in the input image, we'll get a very high activation. If we don't, then we'll just get 0. So we apply this filter at this location. So what will happen is we have some part of X, but this is not matching, these two are not matching. So it's just element wise multiplication like we did in the convolution operation we saw in the last slide. So it's just counting how many pixels are matching. So 4 of them are matching, right? These 3 and this one. So that's just one convolution. Then we will apply the same filter at a different location. So we'll try to find that pattern in a different location in the image. And so on and so forth. So this is just a demo for that. So this is the input image, and it could be like any input volume in the intermediate layers of the CNN as well. We'll apply this kernel, and then this is like the activation of the feature map which is going to be generated. So you observe that in that sample example we discussed like a couple of slides back, we started from 32 cross 32, then it reduced to 28 cross 28, then 24 cross 24. Similarly, you can see that we are starting from 5 cross 5, we just have 3 cross 3. Right? So the spatial actual extent it's reducing as we move on. Now, let's see like another example, try to understand it a bit better. So let's say we have this filter and we are looking for this kind of edge in the input data. So this is the visual representation, that's fine. If we convert this to pixel values, we'll have something like this. So all of rest is 0. We have like high values at this location where we have this shape. And let's say this is our input image. And let's say we are applying that kernel at this location. So what will happen? So we crop this out, so we call this receptive field. So receptive field is like when you're applying convolution, what's the area in the input image the kernel is looking. So that's it's actually a technical term in CNN. We call that receptive field. So it's easy like for you to understand that in the first layer, because you know that if the kernel size is 5 cross 5, that's the receptive field. But what will eventually happen is, let's say your network is 10, you have 10 layers in your network. Then in the 10th layer, if you're applying kernel at some location, it's actually not looking only at that location, because the feature at that location are actually computed based on a bigger receptive field in the input image. So the actual receptive field is much bigger than what is being applied at that layer. So that's just a technical term. So in this case, the receptive field is, and that's the feature map for that. So if we have some values here, it's pretty high. And that was our kernel again. So we'll have to apply convolution. So what will happen? We'll get a very high activation values, right? So it means that the kernel was able to find that pattern in the input data. Now let's say the kernel moved to a different location. So the receptive field change, and at this location, these are the pixel values. And we'll apply the same kernel with this location. So what will happen? Sorry?
The activation will be low.
Can you say louder?
The activation will be low.
Will be low, right? Because the pattern is not matching. So it will be almost 0. And that's how like CNN works. So that's the basic operation. There is nothing like extra. That's the only operation. Yeah.
So when you mentioned the receptive field, you mean by receptive field, the other way to look at it is that input to the filter, right?
Input to the filter. Right. Receptive field, it's just like where the filter is looking. Because if the image is too big, if it's like the initial layer, the filter cannot look like the full image because it's pretty small. And if we have bigger filters, which is actually looking at the full image, then that will not be very meaningful. because then we can't have too many activations. The kernel will fit like the full image, we will not able to slide it like at different locations.
I guess I'm missing. So are you differentiating the kernel and the receptive field? Or are they the same?
No. Receptive field is different, kernel is
Okay.
different. So kernel is something which is like applied on the input data, and where it's applied, that's receptive field. Okay, so any question on this? Yes.
How do you select the filters value?
The filters. So initially you randomize them like with any values, like a random initialization, and then as you train your network, the kernels are being learned. So you learn those kernels. So when you say you are training a network, you are actually learning those kernels.
In your experience, what's the largest number of filters you've seen a convolutional layer in a neural network have? What's the largest number of filters you've seen? In the previous slide there were 6, but
Yeah, that
What's-
was just an example.
6 is the maximum?
No. 6 is pretty small.
Okay, what's the maximum number you've seen?
Maximum, I think people have tried crazy things. So I think in one paper they tried, I think 5,000 or 6,000 kernels, but that's too high. That's not normal. Usually that depends on like where in the network you are. So in the initial layers, you try to learn less number of filters, and it can vary from anywhere from 64 to 512. So ideally people start with like 128, could be 256, and then as you go on deeper you can have 512, 1024, but I think 1024 that's the max, like in the standard networks. But depending on the problem you're trying to solve, you can have as many as you want. So the limitation is if your input image is too big, right? And you have too many kernels in the initial layers. What will happen is that will generate too much volume. So you will have memory limitations. So if your input data is too big, then initially you should have less number of kernels to avoid that. So that's like one intuition. The other intuition is in the initial layers, what happens is you try to learn very primitive shapes, right? Edges or maybe curves, very primitive shapes. So you don't want like too many primitive shapes. So that's another intuition, you should have very few kernels in the initial layers. And the later layers try to learn complex structures. So, but there can be many complex structures. So it's good to have like large number of kernels at there. Again, for the memory thing as well, as you go in the network, the size of the volume of your features, it actually reduces a lot. Then you can afford to have multiple kernels. So that's another way to look at it. But again, it depends like what problem you are solving, what kind of input data you have. Okay. Any other question? Okay. Now this is just one demo, and so if you see this input image, if you observe the kernel, so the first kernel is like edge slightly towards the left, and the second is edge like again slightly towards the right. So what's happening is in the activation you will see like it's detecting all the edges which are like towards the left. In the top image it's detecting all the edges which are slightly towards the right. So depending on the kernel you are applying, your activation map will differ. Alright, so the question you asked, so I think this will also clarify that. So in the initial layers, what we try to do is we try to learn low-level features. These could be like primitive edges or features like that. And that's why we use like few kernels. The mid-level features, as you move on, the structure like it grows, it becomes more complex. And if you go further in the network, then it becomes more complex. So to learn these complex structures, because there can be like many, a wide range of these complex structures, you need like too many kernels. So that's like one explanation. Alright, so now you saw that we started with like 32 plus 32, it was reducing to 28 and 24, and so let's try to understand how that's happening. Let's say we have an input image 32, 3, then we have 3 cross 3 cross 3 kernel. Again, this 3 should match the depth of the volume. And the reason is when you are applying this kernel here, you are striding or moving this kernel across the spatial domain. You are not striding it across the, we call that channel, along the channel. So it will have to match with this. So you do the convolution, you get just one value, and if you convolve like at all the locations, you get this. Now let's look at this example. Let's say your initial feature map is 7 cross 7, you apply a 3 cross 3 kernel. So you can apply it here, right? Then you can move by 1, move by 1. So you can move like 5 times, right, if it's a 7 cross 7. And similarly, in the height as well, you will be able to get only 5 activations. You can strike only by 5. So this is a simple formula. You can derive this. It's not like very difficult. If your input size is n, your filter size is f, then you will get these many activations. And that's the reason, like, because you can have that many activation as the input size, your spatial, the dimension of the feature vector was reducing as you were convolving features. Now what we did here is, when we move our kernel from one location to another, we actually just shift to the next location. So we call that stride, and that's a parameter in your CNN, and you will figure this out later. So that was stride of 1. You were not missing any location, you were covering everything. The other variation could be, you can skip one location and then move forward. So we call this stride of 2. Similarly, you can have stride of 3, stride of 4. It depends like what problem you're trying to solve. And depending on that, what's your stride, that will like decide what's the size of an activation map which you get. So that's the simple formula. I mean, if your input size is n and your kernel size is f, you're using a stride of s, that will be shape of your output feature map. You can have a stride of 3, but it doesn't perfectly fit it, right? After this point, you can't have a stride of 3. So not all parameters will be like feasible. You'll have to figure these out like very carefully. What should be your based on what is the input image, what should be your filter size, and what stride you can use. So it all depends. So it's not that you can use anything and it will work. Alright. So just using the same formula, because this is fraction which is not possible, so you can't use this. So you can use actually this formula to figure out what your stride should be if you're trying to control like what volume you want in each of your layers. Now what we do is, if you want to preserve the spatial dimension of your volume, your feature volume, there's this thing called padding. What it does is, it actually adds 0 values in the borders, and in this way what will happen is, you will be able to add as many activations as there were in the input feature map. So if you want to preserve that volume, the shape of that volume, you will have to do padding. So 0 padding is one way. There are many other ways, like you can use the neighboring value, you can take average, but usually you do 0 padding, that works just fine. So in this case, so you can update that formula. So if you include padding as well, so it becomes n minus of plus 2p, and then you can get your shape of your output feature map. So if you want to preserve the feature map, you can use like you can use whatever kernel size you want, but then you'll have to pad this appropriately. Like say if it's a 5 cross 5 kernel, then you may want to like pad it twice to just get activation for this location. And if you use a stride of 1, you can always preserve your like a feature volume. So it doesn't matter what your kernel size is. You can always do that depending on what kind of padding you're doing. Okay. So coming back to your question, you were saying like how many kernels you should use. So if you keep preserving your feature volume, then it will require lots of memory, right? And I showed you like in the later layers of the CNN, you're trying to learn complex structures, right? So complex structure, it can't be present like in every pixel location of the input image. If you're saying it's a complex structure, it means it's kind of representing a bigger portion of the image, not just like few pixels. So for that, what you usually do is you try to reduce your feature volume size as you move on. And using convolution for that, it's not a good idea. I mean, there are many different reasons, but that's fine. You don't have to worry about that right now. But the good idea is you should preserve your feature volume. But if you want to reduce the size of the volume, pooling is like one operation which you can use. And pooling means like, let's say if you have a 4x4 feature, and again pooling has a kernel size. Let's say the filter for pooling is 2x2, it means that it will be applied at 2x2 pixel locations. So what it does is it will just pick the maximum activation among these 4 values. So 6 is here. Again for this you have 8, 3 and then 4. So what it will do is it will take the maximum activation you have in the input feature and just preserve that. And it will reduce the feature size to half. And not just half, it depends like how you are performing pooling and what's your stride, what's your filter size. You can also reduce this to like 1x3 if your kernel size is 3x3 and you take a stride of 3. So it depends like what's your filter size, what stride you are using, and that will like tell you how much you can reduce further. But usually in all the standard networks you will see like it's usually making it half. So that's the standard. So this was just like a flat one activation that's showing you the full feature map, and that's what will happen after pooling. So it's similar to downsampling you do in your images. Yes.
Why is it always maximum, like not so much average? Why do you use maximum pooling and not average pooling?
Yeah, so this one is max pooling. You can have average pooling. You can have mean pooling. So.
But why is it all like no? I always see max on networks, and I'm always wondering why max?
Why max? Because so activation is saying like whether you have that structure in the input or not, right? So when you're taking average, again it's hard to explain, but based on my experience, what's happening is when you are averaging, you're kind of messing up with the activations. So let's say you found one edge,
Yeah,
right?
Makes sense. Yes.
But again, that might not be entirely true, but that's just one intuition that might be happening. There are many other factors. Sometimes like average pooling do perform better than max pooling. So it depends on the problem. But most of the times people usually just use this max pooling and it works. So CNN we have convolution layers, you know that. We can have pooling layers, that's fine. The other interesting thing is activation functions. So you will see like you usually use activation functions along with your convolution layers. And you need activations because what's happening is when you're performing convolution, you are doing element-wise multiplication, summing those and getting activation. So if you keep doing that, some of the activations might grow very, very large, right? And some of them will be almost zero. So there's a huge range of that, it will be disbalanced. So you don't want that. So to control that, what you do is you apply activation, and it just means that you normalize your input data. And if it's like ranging from 0 to maybe 100,000, you don't want that. Maybe you always want that your data is between 0 and 1. So you can normalize those values, and there are different activation functions to do that. And let me go through those. So you have sigmoid, it's just a sigmoid function. It will ensure that whatever the minimum value you have in your activations, it will be close to 0. And whatever maximum value you have, it will try to bring it to 1. So everything will be 0, between 0 and 1. Tanh is like if you want your values between -1 and 1. ReLU is something which again makes between, so the minimum it clips to 0, but maximum it doesn't care. It will just keep that value. And usually ReLU performs better than the other two in most of the scenarios. But again, it depends. Now, usually I think you will not care like what activation you are using. You will just use like the default one. But there are few places where you will have to be careful. And so some of the cases are, so let's say you are working on image classification, right? And image classification, if you're trying to predict probabilities, then you know probabilities between 0 and 1. Then you want to make sure that your final activation is sigmoid. And you can't use Tanh and then say that you're predicting probabilities, because it will also give you negative values. And you can't use ReLU and say you're predicting probabilities. That's not right. So that's just one instance, and there will be any other cases as well. So another example will be, let's say you're trying to do image or video synthesis, right? So you're trying to generate image. Then depending on in what format you are trying to generate, your values could be between 0 to 255, or it could be between 0 to 1, and you will scale them back. So in that case, you want to make sure that you are using the right activation. So you can't use Tanh. If you're using Tanh, then you'll have to scale this -1 to 1 between 0 to 256. So these are like very trivial things. I mean, if you know, then you will not make these mistakes. But if you are new, then you will definitely make these mistakes and you will not know what's happening. So be careful like what activation you are using. So this is like one scene. I think this is AlexNet. This is just showing an input image and all the activations along the layers. So in this one we have convolution operation. So this is the actual activation map which we'll get by, it's just applying like one random filter which we learned. And this is like after applying ReLU. You can see the transformation. It's actually clipping all the negative values. Again the activations, ReLU. Then it's actually pooling, making the size smaller. And this is as it goes on. That's the final prediction here. So let's try to like understand this AlexNet for those who don't know. So this was the actual structure. The input size they took was, it was actually 227. In the paper they showed 224. That was just a typo. I just like take this figure from the paper, so I didn't modify this. But this should be 227. So the input was 227, 3 channels RGB. And in the first layer, they used kernel 11x11x3, and they use it with a stride of 4, and they only use 96 filters. So using 96 filters, stride of 4, that's the shape they get. And so yeah, they have 5 convolution layers, 1, 2, 3, 4, 5, 3 dense layers. After the features, they just flatten it. These are just a neural network, and then make the prediction. They were trying that ImageNet. So ImageNet has 1,000 classes, so 1,000 predictions. And so let's see conv1. That's the input image. So we have 96 filters, 11x11, and they were applied at a stride of 4. So that's the formula we know of. It will give us 55. So the shape will be 55 cross 55 plus 96. So now, as I like told you earlier, these kernels are something which we are trying to learn when we are doing training. And rest is like just data flow. So for this convolution layer, how many parameters do we need? Like how many parameters we are learning? Yes.
Only 11 by 11 by 3. Well, times however many chromes they had, 96. Yeah.
Right. So we are learning those kernels, right? So the shape of that kernel and how many kernels you want. So those are the actual parameters we are learning. So every time we train a network, we will update those values. And once the network is trained, those are actually network weights, which we will use to actually make the inference about input data. So it will be 11 cross 11 cross 3 equal to 96, around 35K. So after con, they have a pooling layer, 3 cross 3 filters, they were applied as right of 2. So the output volume, again you can use the same formula, it's 27. And so how many parameters will this layer have? So we have these many filters. This is the stride.
Are you asking for the size of the activation layer?
Yeah, so that's these many activations. So that's the input. And then we are applying max pooling at this location. So the max pooling here has 3 cross 3 filters and we use a stride of 2. So the question is like, so output is fine, we'll get 27 cross 27. The question is how many parameters we'll have in this layer. Sorry? Yeah. Sorry? Can you say it louder? Right, there won't be any parameters. So pooling, it's just taking activation values and taking the maximum if it's max pooling, average if it's average pooling. So we don't need any parameters. Right? So we won't have any parameters in max pooling layer. Similarly, we won't have any parameters in the activation layer, because it's just normalizing the activations. So we can actually go through like this, and it will be a good exercise for those who are like looking at LXNet for the first time. This will give you an intuition like what exactly you are actually trying to learn in a network, and how many parameters you could have if you build such kind of network. So I have just summed this here, and so the first one we just saw 35K, we won't have any of this, these two, 307K. So you will see like as we are increasing the number of kernels, the number of parameters are increasing. Yes.
Why is it better to have the 3 fully connected layers instead of just doing one fully connected layer at the end with 1,000 neurons?
Because, yeah, I mean, your question is genuine. We don't do this anymore.
Uh-huh. Okay.
And this was like, they use this. So there are multiple things. The first thing is having fully connected layers, you have too many parameters. So that's good, and that's also bad. Good because you can learn like more complex things, right? And it will be good if you have a very big data set, very complex data set. But what usually happens is if you have a very simple data set, it will just learn everything, memorize everything. And we call that overfitting, right? So that's not a good idea. And if you want to optimize your network, we usually don't use that many fully connected layers with that many neurons. So we want to avoid overfitting. And in the recent networks, so you already know, like, so you don't have fully connected layer, they just use convolutions. They have just replaced it with convolutions, which is like more generalized, and it won't overfit, it has less parameters. So even in this case, you will see like the maximum number of parameters are coming from these fully connected layers, so that's not good. Alright, so that was the structure of the LXNet, and there are many other things which I haven't covered yet. So before I go through those, any question on the architecture? Anything which wasn't clear? Yes.
Not exactly any doubt, but want to know that how it is decided that how many fully connected layers are required. Like the first layer is obvious, we'll flatten all the feature maps better towards the end of the network.
Mm-hmm.
But post that, the number of fully connected layers, the first layer is decided at 4056 LS.
Right. Uh-huh.
But how is the next layer decided? It would be 4096 or less than that or smaller than that?
I mean, that's just a design choice. I mean, you can have any number of neurons. So it's similar to like your standard neural network. You can decide how many neurons you want.
So how is that decision maker? I think that it won't be like a random decision to be made.
Okay. So there are a few guidelines. One is, as I said, we don't use fully connected layers anymore. We just replace this with like 1x1 convolutions, and that does the job pretty nicely. So one ground rule is you don't want too many parameters. So you don't want, like if it's 4096, you don't want to have like 10,000 neurons at that location, because these neurons are representing something, and you don't want like more than that neurons to learn something which is simpler. So that's like just one guideline. The other guideline is usually you keep reducing the neurons, because the initial layers is learning the complex structure because it's fully connected layer, right? And then you want to reduce that further so that eventually you have to get to the number of classes. So what I do is, usually what we do is we gradually reduce it. If it's 1000, we'll have 4096, we can have then 2048, and then maybe 1024, and 500 if you want to have too many layers. That's one guideline. But again, so probably I didn't get your question. So did I answer it, or?
Like just wanted to know that basically in my last computer class I had a doubt, like how should I choose that after which fully connected layer should I stop, like x cross the number of classes I should give the output, or how many fully connected layers should be added post the convolution feature maps.
So my first recommendation is like don't use fully connected layers. Fine. Now if you want to use fully connected layers, then depending upon how many features you are getting at this location. I think LXNet gives you 9,000 neurons, and then the other thing is how many computation power you have. If you have powerful GPUs like TPUs and all those, you can have as many neurons as you want because it will fit in memory. So what's going to happen here is, if it's 10,000 neurons, then you're adding 5,000 more neurons. The number of weights is like 10,000 times 5,000. It will grow a lot. So ideally it should be less than your previous layer, and again depending on how many power resources you have, you might want to check like what's fitting in your memory, right? Yes.
Is there some trial and error is also involved in creating the architecture?
Yes, there is. You won't create like your architecture for the first time. It will take some time. So like one thing is like how many layers you want, because you might think like you have come up with a very great architecture, let's design this, but then again it might not fit in your memory. Then you will try to optimize what is like the least important thing you should reduce, and it will be like, I think, the fully connected layer which you will go after first, because that's like the maximum memory consuming part of the network. So it won't go through like in the first step. It will take few iterations. Yes.
What did you say that you replaced the fully connected networks with?
So just 1x1 convolutions.
Okay.
So effectively it's a fully connected layer, because it's going through all the channels, right?
Is that just like a 1D filter?
1D filter.
Okay.
So LXNet being the other parameters it had was like activation, dropout, I think, time time is over. Let's see if we can cover that. So again, batch size is another important thing. You want a good batch size to train your network. If you just pick a batch size of 1, it means you are training with just one sample. So it could be like you may fit a bigger network in a memory, but it will not train very well. So you want a bigger size so that your network trains well, and that might have to you might have to reduce your network size for that. So that's really important here. Batch size. I think we will cover this later as well. These are just other parameters. Don't have to worry about this right now. And we are already 4:11. So I don't know how much more we can cover today. Okay, just let's talk about the loss function. Now, once you have this network, you want to train it, and to train it, you need some input data, and then the network will predict something, and the prediction will tell you how good the network is predicting. Right? Now, you need a metric or a measure which can tell you how good the network is performing at this stage, and use loss functions for that. So your loss function will tell you how good your network is at each step of your training, and based on that loss function, you will train your network. You will update your kernel weights. Okay, so it's a way it will tell you how good your network is, and then given a loss, you have different optimization algorithms which you can use to optimize the weights. What usually you use is gradient descent. We'll briefly cover it in a couple of minutes. So your loss function is, you can have different type of loss functions. That's a research area in machine learning. So don't worry about how to come up with loss functions. So let's say you have a loss function. The input to that is the input, your data, your image, and the network weights which you have learned so far. So if you use those weights, use the input, you will pass your data through the network, you will get some predictions, and this is just representing that. So you give the input, F is the network, it will give you the output, and this is the ground truth. Ground truth means you know what the image is. Let's talk about classification. If you know that the image is dogs, so this Y will tell you it's dogs, and this F of this function will tell you what you are predicting. So based on what you are predicting, what the actual ground truth is, you can compute a loss. So, and that's your loss function. Standard loss function for classification is binary cross entropy. So what it does is, that's your ground truth, that's your network prediction. So in case of classification, let's say you have n classes, and each time you will have either the class will be present or it will be absent. So this is the positive case when it's present. So if it's present, it will be 1. If it's not, it will be 0. So if it's 1, you can just ignore this, and then that's give you a value. So if you are predicting 1, if the ground truth is 1, log 1 is going to be 0. Right? 0 means very good. It means your loss is 0, you are doing perfectly fine. The network will not be updated because it's already doing well. Let's cover the second term. This is for the negative case when that class is not present. So if it's not present, it will be 0, that's the ground truth. 1 minus 0, 1, you can ignore this part. Now if you predict 0 for a class which is not present, it's very good. 1 minus 0, 1, log of 1, 0. Again, you are doing pretty good, so it gives you 0. So if you're doing everything right, cross entropy will give you 0, and that's good, nothing will be updated. Let's say it's a positive case and you're doing pretty bad. So bad, then what you will do, you will predict a 0 here, right? Log 0 is negative infinity. You apply this negative sign, it becomes infinity. So your loss is infinity. So what will happen is, it means your loss is ranging between 0 and infinity. If you are doing good, it's 0, it's bad, infinity. So that's like one loss function you can use. There are many other variations, but probably I think you will just use this one. And I think the time is over, so we should end. I don't know if there's any other class or not. I will try to cover this maybe in the next lecture, maybe a couple of 10 to 15 minutes, and then I will start the presentation. Thank you.
Usually you guys